My name is Salman Parvez. I am Associate Professor at Rochester Institute of Technology, Dubai, and I will be presenting this review paper that is related to the current research trends in different variants of MQL technology. A brief agenda of today's presentation. As far as the motivation and goals are concerned, first I will discuss the industrial significance of different modern materials. So during the machining of these superalloys and modern materials, uh, high heat energy is generated, and at the same time higher cutting forces are also produced. As a result of these higher magnitudes, poor surface finish is observed, and at the same time high tool wear is observed. So machining of these modern material, it remains like a costly task because of these problems. And in order to manage the temperature and friction and to lower the temperature and friction, currently industry is using different types of cutting fluids. So as I've mentioned that the industry was employing the cutting fluid in order to manage the temperature and friction during the cutting process. It is observed that there is a harmful effects on environment and on the human health because of these cutting fluids. So there is a need basically that type of lubricant or type of method or technique should be utilized by which environmental burden of the cutting process can be reduced, and the cost of the process can also be optimized. In the current slide, it can be seen that machinability is not a very straightforward thing. It is a very complex function of different parameters. So for example, machine parameters such as the power, torque, or precision or dynamic characteristics of a machine tool, the affects machinability. Also, the cutting tool material and the cutting geometric parameters, they also affect the machinability. At the same time, cutting conditions, feed rate, cutting speed, depth of cut, and the type of environment being used, that is also affecting machinability. At the same time, the workpiece properties, for example, the chemical composition, strength, hardness, strain hardening, all these, they play a very important part towards the machinability of a material. As it is mentioned previously that machining operation has a lot of environmental burden in it. So there is a need to make the machining process more sustainable in nature. And the current slide shows that machining operation can be more sustainable by reducing waste, by reducing power consumption, and by enhancing operational safety. In order to avoid the harmful environmental effects of conventional fluid cooling, minimum quantity lubrication technique is used, that is referred as a green method. And the philosophy of MQL shows that because we are using the cutting fluid in a very small quantity, so as a result of this thing, the environmental burden is reduced. At the same time, the lubrication cost is reduced. MQL technology promotes evaporative and convective heat transfers, and it provides an effective way to cool down the cutting tool as compared to wet cooling. The effectiveness of MQL technology is linked with the high velocity fluid droplets that penetrates the vapor blanket and reached into the tool work interfaces. It helps to provide a better heat transfer than the wet lubrication, and the oil droplets reduce friction between tool and chip, where the compressed air removes metal chips from the machining zone. Also observed that the penetrated oil particles adhere to the machine surface and promoted plastic flow on the back side of the chip. As a result of this thing, machinability was improved with MQL technology. The performance of MQL technology is linked with different parameters. One of the such parameters is the nozzle position that largely affects the penetration ability of cutting fluid into the machining zone. And it is observed in the literature that better penetration of cutting fluid was observed when the nozzle was projected on the flank face as compared to the rake face of the tool. Some other important MQL based parameters are air pressure and oil quantity. Uh, the researchers found that increasing the air pressure value can reduce the tool life, and MQL technology was just acting just like dry machining. However, it provided the better surface finish as compared to dry cutting. The quantity of cutting fluid also affected the machining response. It was observed that an increment in cutting fluid quantity resulted in a better tool life. However, the surface finish was not affected by the fluid quantity. Conventional MQL technique is referred as a lubrication technique. So, because it's a lubrication technique, it takes care of the friction part during the machining operation. Another variant of MQL is called as MQCL, that is a minimum quantity cooling lubrication, where sub-zero temperature air is mixed in the MQL, and the sub-zero temperature air takes care of the cooling part during the machining operation. There are some studies in literature that provided the effectiveness of MQCL technology. So, for example, in this current work, Murada machined the AISI 1025 steel using P25 cemented carbides, and he examined different cutting environments such as dry and MQCL. And his experiments showed that when MQCL was mixed with the phosphate ester, it reduced tool wear by 40% when it is compared with the dry machining. In another study, MQCL performance was investigated for the machining of titanium alloy, and the different oil flow rates were investigated, and the performance was compared against the dry and flood cutting. It was observed that the optimal performance was achieved at 70 milliliter per hour flow rate, and it provided the optimized penetration ability of the cutting fluid. And as a result of this thing, less adhesion and abrasion was received when the tool wear mechanisms were investigated. In another study, multi-jet MQCL assisted machining of titanium alloy was investigated, and the performance was compared against regular MQL and dry cutting. The study revealed that with multi-jet MQCL technique, the temperature was reduced by 20% as compared to the conventional MQL technique. When it comes to the modeling of MQL machining process, computational fluid dynamics approach is used. With this kind of simulation, the flow of the fluid between a nozzle and the workpiece of tool interface is usually examined. The problem of CFD simulation arises in effect that the mechanical properties of solid components and therefore the chip formation cannot be simulated. In order to cater the problem, there are some approaches recommended in the literature. For example, in the current approach, two-step method is utilized. And in the first step, a 2D orthogonal cutting finite element model was developed that provided the temperature distribution. And in the second step, the temperature was used in a CFD simulation, and the interaction of cutting fluid, that is basically in this case a dry air, was modeled using CFD approach. And the approach provided very encouraging results. The major conclusions of this study are as below. MQL supports sustainability and green manufacturing. It provides ecological and economic solution to coolant application, and it has a potential to replace the conventional flood cooling. In MQL, lubricant evaporates, so cutting zone remains dry, which is again an advantage over flood cooling method. Improved tool life and surface quality at reduced temperature. Did not achieve comparable chip evacuation like wet cooling, and it is not suitable for grinding, deep drilling and awning operations. As a future work, MQL parameters needs to be mathematically analyzed. Another future work is that energy, environment and cost should be optimized for the MQL process or MQL variants. and more efforts are needed basically to couple the finite element and CFD models for more reliable results.